Good afternoon, everyone. This is lecture 25 of PTRE 475575, well completions and advanced stimulation techniques. Last time we finished the class by looking at a video about a flow loop in a different university with the different flow patterns from YouTube. And it's not the only video that exists there on flow loops. And if you guys come over for the laboratory classes in the summer, PTRE 462, which actually I teach, there is one session that we look at the flow loop that we have here. It's no longer in operation for how do you call it, research purposes, but it's still there. The student who built it and used it for his PhD graduated, and it's sparingly used now. But we can run some water and air, we can see some of the patterns. Your TA knows how to use it pretty well, I would say. So yeah, I mean, remember that all those stuff are empirical. So it's like you make experiments and you decipher the results. There is then the applicability of that really varies, and there is no way to derive mathematically expressions for these multi-phase flow patterns. Anything beyond Buckley-Leverett. Buckley-Leverett is the only fully analytical solution that you can find. You'll see people with that have research experience on this matter. Many times they will struggle to answer the question if there is anything beyond Buckley-Leverett that does not include empiricism. Actually, the answer is no, it doesn't exist, as far as I know. And of course, Buckley-Leverett, which is what you learn in reservoir, immiscible displacement of two incompressible fluids, no capillary pressure, no interference. I mean, you can include capillary pressure, but it's a highly idealistic scenario. It works really well when you do core flats, because when we do core flats in the lab, we take a small core, which is 2 inches in length, 1 inch in diameter. We put it in a core holder and we flush fluid through it. And that flushing of fluid approximates as one dimension. You can ignore the movement of fluid on the side. So you consider only the fluid motion into direction along the length of the core. And then you have this, you can compare that with the mathematics quite easily. And we have students that have done that in the past, actually. It's not just here, in many schools. But yeah, I mean, that's as far as the math can take you when it comes to multi-phase flow. Only very idealistic stuff, idealistic conditions, etc., etc. Now, we will move to a topic that is related to a class that you took maybe a little bit further ago than production, something called petroleum fluids. I don't know the full name of the course, but I know that Dr. Alamuti is teaching it, and you guys are using the McCain book. I forgot his first name, from 1990. And it's a very nice class. So we're going to talk a little bit about reservoir fluid classification, which again is something that you had already seen before, so it should be an easy topic. And because we are gradually moving from multi-phase flow to PVT now, because all those aspects of a reservoir fluid affects the way you are going to produce it. It affects the completion hardware that you need to input in your well. It affects the way you want to produce it. And we're going to talk about some stuff. Again, it's nothing that you haven't seen before, in all honesty. The type of reservoir, its composition and phase behavior can impact well performance, completion, stimulation, decisions, etc., etc. As much as the reservoir, actually, the reservoir rock. I mean, we do hydraulic fracturing because the reservoir rock has very low permeability, but also the fluid matters as well. There are cases where the way you produce the well, you control the bottom hole pressure. The lower you make it, the faster it produces. If you remember from the IPR curve that we saw in the previous slide. Okay, you lower the bottom hole pressure, and the more it produces, the more it produces, the more it produces, and then it goes to the absolute flow, open flow potential, which is like the top speed of a car. We said it's a hypothetical value at atmospheric conditions, like the bottom hole pressure of the reservoir is at atmospheric conditions. There is people who's there is techniques that, or if you are lucky to be in a well that to have a well that allows you to play a little bit with bottom hole pressure. You don't get too much sand production when you lower it, etc., etc. You can vary the pressure in a way such that the composition of fluid that comes out of the well is favorable. Like if you want to go after the heavier fluids, the heavier components of the oil of the reservoir oil, you maybe want to play a little bit with the bottom hole pressure to increase the proportion of the heavy fluids in the blend that comes out of the well. And of course, we need to remember that unlike the way we simulate the reservoir many times, the reservoir fluid many times as one fluid, crude oil or reservoir oil is a blend of fluids. It has different components. It has light components like methane, ethane, propane, more mid-range, butane, pentane, hexane, and then it has heavier ones, heptane, octane, nonane, decane, and so on. It also has some impurities like CO2, H2S. Those are dangerous. The more CO2 and H2S it has, the oil has, we call it sour. If it doesn't have, we call it sweet. Okay, removing it, we call it sweetening. Okay, CO2 and H2S in particular, H2S, it can mess up things tremendously. First of all, CO2, which is the more mild of the two, mixes with water, makes something called carbonic acid, and starts destroying your equipment, basically. I have seen carbonic acid not only destroying tubulars in a well, I have seen it destroying pumps in the lab. Sometimes there is some pumps in the lab. Generally, the idea is, the rule is, if you're in a big lab with many labs, if we have a pump that is used for gas, it's only going to be used for gas. If it's a pump that is used for pumping water, it will only be used for pumping water. We don't mix the two. If you take a pump that was pumping water, try to clean it up, and then you put CO2 in it, and you try to inject it, you can never clean up a pump completely from water. There will be some droplets left behind, some moisture. it mixes with CO2, makes carbonic acid, starts eating your pump from inside, and then suddenly you start seeing leakages, and that $25,000 pump is for trash, basically. I have seen a young professor to do that, actually. Ignoring this, he spent his funding money to buy a set of pumps, and then he was eager to test. He was running them with water, and then he was eager to put gas. And oh my God, it was so bad. I saw when they opened them, it was so bad. H2S is even worse than CO2. CO2 is okay. Yeah, it has its disadvantages, but H2S is very bad. It's also poisonous in low quantities. It's a hazard in field operations. If you are in a well, if you go to a rig and you pass, in America, there is a sort of a stand as you enter the rig, and it says if there is H2S danger, and if it's a green flag, you are good. If it's a yellow flag, it's like maybe some people who are nearby the rig, they need to wear a mask. If it's a red flag, yeah, it's like everybody needs to wear a mask, and only qualified personnel should be there. What else? There is several oil field services company, like some of the ones I worked with. They have a rule in their contract. If they find H2S as we are drilling, we leave the place. We don't stay there. So we basically stop taking readings. We stop doing the job that we are supposed to do if they find H2S. And people in the field are actually afraid of H2S, and they should be, because it really kills people in pairs. Your body goes down, and then you run to help him, and then you smell the H2S, and then it collapses you as well. And some people, they were wearing a mask, and they still got affected by H2S. They said it was through the ears. I read a study, it was through the ears, they said. H2S is very, very difficult gas to deal with. Also, in several quantities, it's pretty much odorless, and like it doesn't even make a color. If it mixes with water, it gives you this rotten egg smell. But in general, how do you call it? It's H2S is crazy. Yeah, you cannot see. It doesn't have a color. It's colorless and odorless. And it can be detrimental in very, very small quantities. So please take it seriously if you are in the field and you have H2S trouble. We all have to wear our H2S monitor, which is a yellow one. If you are in an oil town, you will see people in the Walmart, United, or any kind of grocery store that is there. You will see them wearing it actually many times because they forgot it on. It really needs to be on your breathing space. The H2S monitor. I have one downstairs, but it's dirty. It's dirty with oil-based mat. And every few months, you need to bump your H2S monitor. When you start working for a company, they are gonna give you one, and then they will basically replace it after some time, according to their policy. They have to comply with the policy, and you guys need to take a safety class every year, basically. For a big component of that is H2S. Now, if you are gonna be working with H2S, there is some additional things that need to take place, like you need to be shaved, clean shaved, so that they can put a mask on you. And the mask should be fit and tested. And they fit test the mask when you go for safety training. It's a separate class that you have to take. There is some issues like people who have a scar, a big scar on the face, sometimes the mask won't fit very well. I have heard stories. I think every attempt that they make for the mask to fit, it gets recorded. And if it's a failed attempt, you cannot erase it. So there was somebody who needed the job very well, very much, and they tried to fit the mask 37 times, 37, and all of them were unsuccessful. And then he tried to give them money to pass him because he really needed a job. And they were explaining to him that all those attempts are recorded, so there is no way we can, and that they can accommodate that request, I guess. But yeah, I mean, it's somebody else I heard had a very weird shaped face. And I don't know what that meant, but the mask wouldn't fit very well on him. But yeah, it's and the H2S is a little bit like the sun. Like if you get heat stroke once, then your tolerance for the heat, for the sun drops. Same thing with H2S. If you get hit by H2S and survive it, your tolerance goes down. So next time you're gonna be hit earlier at a lower level, etc., etc. And there is all sorts of standards that you need to. Well, I had them memorized when I was young, but I don't remember them right now. Above this level of ppm, it gives you a headache. Above this level, it makes you dizzy. Above this level, it does that. Above this level, ppm, it's killing you. ppm is parts per million. So yeah, I mean, and also the refineries, they don't want to be dealing with H2S. They can, but they don't want to. A lot of the oil that is coming to the US from Venezuela, even before the Maduro capture, people were wondering why does the oil from Venezuela is coming over to the US for refining, whereas we send our refining, our oil, which is better quality elsewhere, is because our refineries here have the capability to deal with these sour fluids more than in other places. And our oil that is easier to deal with, we send it abroad. It's sort of a dynamic, market dynamic that was created a long time ago, well before the nationalization, the last nationalization of Venezuela, which was 99. But yeah, I mean, you really, H2S can cause a lot of trouble. And yeah, I mean, whether in the reservoir fluid or out in the air, yeah, very, very, very dangerous. So we need to know about this stuff in our wells, in our fluids, so that we can design our wells accordingly. So reservoir fluids are classified in 5 categories per McCain. Those are black oil, volatile oil, retrograde gas, wet gas, and dry gas. And there is another category called dead oil. It's sometimes used separately. Dead oil means oil without any gases in it. Okay? Live oil is often called like black oil, volatile oil. Together they are called live oil. It's like oil with gaseous components in them. The classifications are based on things that you should already know, like API gravity, which is related to density, gas oil ratio, GOR, formation volume factor, composition, and so on. Phase diagrams is basically a plot of pressure on the vertical axis and temperature on the horizontal axis. And these are used to display what we call phase behavior of the petroleum fluids from initial conditions to surface conditions. A little bit of a parenthesis here. I don't know how it's done at UND, but I don't think we have a thermodynamics class in our department, which is a sad thing. But you can take thermodynamics from a different department. The thing is that for petroleum engineers, phase behavior is huge in thermodynamics. That's one thing. And secondly, is that the liquids that we are dealing with, I mean, they are much more diverse than other classes. Say if you take thermodynamics from mechanical engineering, oil for them is one thing, you know. Oil for petroleum engineers is 20 different things, you know. So if you have a chance to take a thermodynamics class designed for petroleum engineers, I would suggest that you take it. Even if it looks like you don't need to. If you have good understanding of thermodynamics, I think it's going to help regardless of where you work. You may be doing surface facilities, you may be doing, I don't know, you may be doing well completions, you may be doing production. Thermodynamics plays a very big role. Stimulation, not so much, but does a little bit. I mean, thermal effects play a very big role, but also energy related.
Well, Professor, we took this material in the petroleum fluid properties, PTRE
I know.
311.
Generally, petroleum fluid properties is before thermodynamics.
Yes, was in the freshman, the second year. Yep.
Yeah. And and transport phenomena, those kind of classes. The way the graph is basically we set pressure on the vertical, temperature on the horizontal, and then we have something like that. And this is the two-phase envelope. If you are inside this little ellipse, half ellipse, whatever it is, you are in the two phases. You have liquid and gas. Okay? If you are in the outside, you have single phase, either liquid or gas. And you can move from liquid to gas with single phase liquid to single phase gas by staying without going into the two phase region. It's not very common, but it is possible. It's not uncommon. So when you are into this ellipse, inside that ellipse shape envelope, that's where you have both phases. The important elements that we are going to talk about that I want you to know is cricodentherm. That's the name of the highest temperature of the two-phase region. So this is my temperature, pressure. The cricodentherm, higher temperature of the two-phase region. So how far on the horizontal axis do I go? I think I go like up to here. This is the cricodentherm. What about cricodent-bar? Cricodent-bar is the highest pressure of the two-phase region. So you need to be looking at the vertical axis for that, not the horizontal axis. So it's something like this one. Cricodent-bar. Remember, bar, the unit of temperature, pressure, and third, temperature. So those are important points on the two-phase region, as well as the bubble point, which is the conditions over which the first gas bubble formed, the dew point, which is the conditions at which the first liquid forms, and then the critical point. So I'm going to show all this together because they are all related. So we showed pre-condensed therm, we showed pre-condensed bar. Let me make this critical point. Critical point. Let's just say this one here. It's arbitrary. I drew it arbitrarily, but it can be further to the left or further to the right along that ellipse. Now, that critical point indicates difference in two lines. Let's see. You have on its left, you have this line along the ellipse, orange. And on the other side, you have the yellow. The critical point tells you where the yellow becomes orange, stops being yellow and becomes orange. Okay? So now the way you need to think about it, what happens when I cross the orange line? So I am here. High pressure, certain temperature, low temperature, and then I move here. Lower pressure, same temperature. What do you think happens? I go from single phase something to two phase. So I know that two phase is going to be liquid and gas. Is my single phase where I started from single phase liquid or single phase gas? Do you think?
So from liquid.
Yep, I agree. Very nice. So I went from liquid to liquid and gas. So what happened is that the first bubble came out of solution when I crossed that orange line, right? So let's call that orange thing, orange line, the bubble point. Pressure. Now let's go here. I have high temperature, certain pressure, and I move here. Same pressure, lower temperature. What happens?
So from vapor state to mixture state.
Yeah, two phases. Yeah. So yeah, that's when the first liquid drop comes out of solution. We call that the dew point. And between those two lines, we have the critical point. Now, those lines, critical point was with purple, right? There you go. So those lines now that we saw, okay, they have a certain, oops. Those lines have a certain, they are the outside lines. They are when you go from 100% liquid for the bubble point line to 100% liquid except one drop of gas. And then you go less, you go 99% liquid, 1% gas, 98% liquid, 2% gas, and so on and so forth. So those lines, inside lines, are going to all touch the critical point, and they're going to be like this, and so on. Same thing with the dew point. They are like this, like this, like this, and so on. I go from 100% vapor or gas and one droplet of liquid to 99% gas and 1% liquid, 2% liquid, and 98, and so on and so forth. So the two-phase envelope has a lot of lines in it. So, and it's going to become clearer now. Let's see the black oil, which is an easy one. Okay, with the red line is the bubble point curve. With the green line is the dew point curve. Just like Shamel said earlier, it was orange and yellow. Now it's red and green. Red because red indicates gas. That means first gas bubble coming out of solution, and then dew first like oil droplet coming out of the solution. So with this point here, this is where my reservoir is, okay? And as I produce it, the pressure goes down, and then temperature drops a little, and we get here. Temperature, it's not so much dropping, a little bit, but pressure dropping a lot. So I start from single phase liquid. In the reservoir, I only see liquid. And then in surface conditions on the separator, which is sitting on land, onshore, on the, how do you call it, on land, in the field, that's where we have the conditions. It's basically almost atmospheric conditions, a little bit higher atmospheric. So in the separator, I have liquid, gas. So I need to have a separator, a tank for gas. Oh, sorry, not a tank for gas. I need to deal with gas, send it to a pipeline or something, and deal with oil. Oil is much easier to deal with. Gas, if I don't have anywhere to sell it, I might as well flare it. Because if I flare gas, I convert it from methane to CO2. And there is a big advantage in that it doesn't, it's not flammable. CO2 is not flammable. So if somebody lights a cigarette near CO2, nothing happens. But if somebody tries to light a cigarette in next to CH4, there is wells that leak CH4. It's not a smart thing to go near the wellhead and light a cigarette. It's going to make you an astronaut. But yeah, I mean, not a good idea. There was somebody who tried to light a cigarette on top of a tank. I think he was for a service company. And oh my God, it was so bad. I mean, because you know the fumes coming up, they are all flammable. API gravity for black oil is less than 45 degrees API. Remember, degrees API is degrees API is 141.5 divided by gamma minus 131.5. Gamma is the density of your fluid divided by the density of water at standard conditions. So if your fluid is water, gamma is 141.5 divided by 1 minus 131.5 gives you 10. So the API gravity of water is 10, it's not 1. And then if the fluid is heavy, gamma would be very high, API degrees would be very low. So Canadian heavy crude, Venezuelan heavy crude, they all have very low numbers. They all exhibit very low numbers of API gravity. Now, West Texas Intermediate, which is very sweet, looks like sweet tea. It's 39.6 degrees API. Pretty light, lighter than water. So less than 45 degrees is black oil. Gas oil ratio, less than 2,000 standard cubic feet divided by stock per barrel. Has a pretty low gas oil ratio. Or 2 MSCF divided by STB. Oil formation volume factor, which is the opposite of expansivity factor, is basically how much does it shrink by going downhole, or how much does it expand by coming up from the reservoir to the surface. But taking into account the gas that leaves, the fluids that leave the mixture, because you are gonna end up having gas and liquid from the same, like 1 barrel of liquid from the reservoir is gonna be only half when it comes up to the surface, because it's gonna lose a lot of components. That's how you need to be thinking about formation volume factor. The heptanes plus concentrations, this is often reported differently, separately on its own, is bigger than 20%. So more than 20% of the fluid is made by heavy components. C7, C8, heptanes plus. And separator conditions on the surface have to deal with 2 phases. Okay, any questions on black oil? Okay, I think it's not new. Second one is volatile oil. So the phase envelope looks very similar to black oil, with a small difference that you may not catch unless you check it well, and that is the movement on the temperature is a little bit higher than before. We still lose a lot of pressure, but we also lose a lot of temperature. And the critical point on our line, the critical point and the line is closer to each other. Is closer to each other. So the critical point moved a little bit to the left. The envelope became slightly bigger. And our line, moving from reservoir conditions to surface conditions, moved further to the right. So our line and the critical point got closer to each other. Now, this is a more gassy liquid, okay? It has more gas components in it, but still on the reservoir is just liquid. You know, it gets more gassy as you make it, as you get to surface conditions, separator conditions. API gravity is bigger than 40. Notice there is an overlap, less than 45 for black oil, bigger than 40 for volatile oil. Those are intentional. There is oils that it's very hard to tell, crudes that it's hard to tell what is it. It could be black oil, it could be volatile oil, it could be people disagreeing. And without any of them making a mistake, it could be people disagreeing about, it may look black oil to you, but it might look volatile to me, you know? That's why we use the McCain classification system. Some people use different names. Some people call it near critical point oil, near critical point gas. But we use McCain. Gas oil ratio from 2 to 3,000 cubic feet per stock tank barrel. Oil formation volume factor bigger than 2 reservoir barrels per stock tank barrel. By the way, trick question. Can oil formation volume factor be less than 1? The answer is no. It cannot be less than 1 because it really means that you have a reservoir that is pressurized below the atmospheric pressure. The more the gases, the gas components in the liquid, the bigger the formation volume factor. Okay, because those things are going to be removed when you come from the surface. They're not going to stay there as liquid. C7 plus between 12.5 and 20%, and initial reservoir conditions are closer to the critical point than in black oil. This is an important point. Initial reservoir conditions are closer to the critical point than, so compare this and this. To, and look, I left them there. Let's use different colors. To this and this. Much closer for the volatile. Also compare this, where it cuts the bubble point, to this. And then compare this and this. The yellow is much closer than the blue. Together. That's an important one. Any questions on volatile oil? Okay, now it's going to be a little bit of a difficult one, or more difficult one. Retrograde condensate. This type of behavior, retrograde condensation, was identified by a Dutch guy called Johannes something that starts with K. I don't remember the name right now. I remember that it was the semifinal of Pedro Ball 2015, and we were playing Delft University from Netherlands for the semifinal for a position in the final. And they asked this name, and I was like, I remember this name. And then it's like, what an ironic thing. They're asking about a Dutch person to a Dutch team. It's like we have a disadvantage. And then I was like, but that name I heard before. And it took me a few seconds, and then I was like, oh my God, yeah, retrograde condensation. That's what he discovered. And we got those points. And I remember they were looking at me, the other team, I turned around, they were looking at me very, very surprised, let's put it this way. And halftime, they had a negative score. So halftime we were like 63 to negative something. I remember telling my teammates that they have if you look at them, it's like they had lost already. You know, they just wanted it to be over with. But anyway, yeah. Retrograde condensate is a weird behavior. It's a bizarre kind of behavior that is looking backward, retrograde, like it goes back to liquid. That's what it says here. We go back to liquid condensate. It is not a good thing. It makes it more difficult. In Peru, they have a lot of reservoirs like that. In Algeria, near the desert, they have a lot of reservoirs like that. They are in areas of thermogenic gas. they have a lot of this retrograde condensate behavior. And it's like it's the name of a behavior. So what happens is that I start from gas. I drop the pressure and the temperature. Okay, like this, like this. As I enter the two-phase region, now I start getting liquid. And then I get more liquid, and more liquid, and more liquid. And then I start getting less liquid, and less liquid, and less liquid again. So when I go from zero liquid to more liquid, and more liquid, and more liquid, and then less liquid, less liquid, less liquid, that liquid that was created, and I really want this liquid. This is what's going to give me money. This is what I'm going after. The gas is of secondary importance, financially speaking. It's going to be lost in the reservoir. And it's very, very hard to recover. Very, very hard to recover. So what people do, and they do that in Algeria, they do that in Peru, we do what we call liquid blocking. Liquid blocking. We drill wells around the well that is producing, that we tend to produce from, and we inject, trying to maintain the temperature, the pressure in the reservoir within the conditions that is gonna give us the most liquid so we can get it out. It's very, very hard to maintain liquid blocking. You can get it to work a little bit, but it's very easy to lose it. And they need people like you guys who are smart and understand how reservoirs behave to teach them and tell them what to teach them, like to do the job for them, like tell them, now you need to inject at a higher pressure from this well, lower pressure from this well, bigger pressure from that well, smaller, and so on and so forth. This is how basically it's done. It's the hardest of all classes of reservoir, retrograde condensate. But when I say hard, challenging, as in challenging, it's an opportunity for smart people like you guys to optimize this production, maximize liquid production from retrograde condensate gas. This is how it works. So it's like we start from gas, we cross the dew point line, we get the first droplet of oil, liquid oil coming out here, then more, and then less. So you need to keep it at the region where it produces the most. So we are really going to try to achieve that with liquid blocking. It's almost like doing a water flood, but from all around the directions. And then you want to keep the pressure at a certain range. And sometimes that range is very small. It's very difficult to nail it, you know? API gravity between 40 and 60 API degrees. GOR between 3,300 and 50,000. So big range of GOR because of the way it's behaving. Heavy components, 12.5%. Difficult to bring this condensate to the surface, likely lost into the reservoir. We don't want that. But I took a picture from the book to make it clearer to you guys and see how that works a little bit more. It's from the book of fluids, page 154. Must be chapter 5 or something. So this is how it looks like. The two-phase envelope looks like. And these numbers that you see here, so we use green for the gas. Oh, we use green for the, sorry, liquid. So this one is green. That's the dew point. And then all the way, sorry, to the critical point. Number 2 wasn't the critical point. And then we use red for the bubble. Bubble point with red, dew point with green. Now I'm starting, in the way McCain does it here, he's like, he ignores temperature changes. So he says it's isothermal. Let's assume isothermal. So temperature stays the same, only pressure changes. That means I'm dealing with a straight line. I start from 1, that's reservoir conditions. I decrease the pressure because I'm producing. I get here. What happens there is that my first droplet of oil comes out of solution. So I still have 0% gas, sorry, liquid, but I have 1 drop of liquid. So it's less than almost 0%, basically. And you read that here, 0%. Then I go lower, I hit this line. This line is 5%. I have 5% liquid and 95% gas. Then this 10% liquid, 90% gas. Then I hit this. What is this? 15% liquid, 85% gas. Okay. Then I go further down in this point here. What happens here is the lines that you guys don't see in this book is like line 416, 17, 18, maybe 19, and then 20. So as I go deeper, lower pressure and lower pressure, I go higher than 50. I go 16, 17 maybe even 18, and then I go back to 15 here. So I went 15, 16, 17, maybe 18, and then I went back to 17, 16, 15. And then if I keep going, as you see, I'm gonna go lower, I'm approaching 10. I go back to like 14, 13, 12, 11, 10, and so on. So all this oil that was created, it was lost. So I don't want that. I want to stay in this region where is the most liquid I can get out of my reservoir. By the way, liquid in the separator conditions, like on the surface, I optimize my production, so I maximize the amount of liquids in the separator. And most of the retrograde gas reservoirs, I want to say everyone. If you have a reservoir, a gas reservoir that can produce some gas, regardless if it's retrograde or not, you always prioritize the oil, okay? Gas becomes of secondary importance. You are not going to design your field development plan based on gas. You are going to design it based on oil. This is what you go after. Gas will be supplementary or it won't mean anything if you are going to flare it. Any questions on retrograde gases? Okay. Now let's go to an easy case. Wet gas. This is my two-phase envelope. I start from single-phase gas, and then I get a little bit of liquid in my separator conditions. Bigger motion, bigger change in temperature than before. Bigger change also in pressure. Gases are sensitive to pressure. Gas oil ratio bigger than 50,000. stock surface standard cubic feet per stock tank barrel. Very high methane concentration. So if you divide them into components, the C1s are going to be very, very high. Surface conditions in separator. What did I do? Sorry. I threw a market out. That doesn't belong to me. Surface conditions in separator are inside the two-phase region, just like any other reservoir class that you have seen so far. Condensate gas, liquid produced in the surface is called condensate, basically. So that liquid that you find in the separator is called condensate. And again, unless it's very small amounts, you are really gonna design your field development plan based on that. The last classification is dry gas. A dry gas is fairly simple. You start from single phase gas and you end up in single phase gas. No changes. You never cross the dew point curve. You certainly don't cross the bubble point curve. And you are gas all the time. You are almost entirely methane or ethane. Mostly like methane. Surface conditions in separator are outside the two-phase region. No liquid phase underground or the surface, neither in reservoir nor in surface conditions. Fairly simple, this one. And these are the classifications from McCabe. And now the big question, which I already answered today, I forgot that I have a slide about it. At this point, people should be telling me, sir, why do we do about this when this is a completions class? And I already answered it, is that these things do affect your completions. The chemical composition is impacted by pressure. Varying flowing bottom hole pressure can influence the percentages of each component in the fluid on the surface. C1, C2, C3, C4, C5. Generally, C3, C4, C5, C2 even, you like those components, you know? If you can maximize those, please do. Some fluids present in the reservoir, like CO2 and H2S, can be harmful to tubulars. This should be factored into decisions on the tubular makeup. For example, in CO2 injection wells, normal steel is preferred as opposed to stainless steel. So if you have nowadays, because cardiological sequestration is fashionable, there is a lot of wells that are drilled for CO2 injection, but not for sequestration reasons, but for EOR reasons. Okay, those wells, they found that normal steel doesn't corrode as fast as stainless steel, which is a weird, phenomenon. But I mean, yeah, if you plan to inject CO2 from your well, from that well, you better make sure that everything in it can handle what you're gonna try to inject. Same thing for production. If you are gonna be producing a lot of H2S, you need to be able to deal with it. So that's when you're gonna think about a shotgun completion, so that you protect your casing. You have a tubular, a tubing that you may sacrifice at some point. Corrosion from H2S is very bad. It's like it causes what we call embrittlement. It makes everything break easier. It weakens the tubular significantly. So you don't want your wellbore architecture to be anchoring on something that will like get corroded. because casing, you cannot really take the casing out of the well and then change it, run new casing and cement it in place. It's not easy to do. So yeah, you need to know what is coming out of the well and what is going in, and make sure that it's compatible with what is inside, what you put in the well. The man-made equipment, the man-made equipment, the man-made tubulars you equip your well with. The purpose that the well was drilled for matters. Is it to produce or to inject, and what fluid? Okay, you may have drilled a well that is going to use for water injection or CO2 injection for EOR. That means it's going to be injecting CO2, but not at high pressure. But if it's for CO2 for storage or sequestration, then it needs to handle a lot of pressure as well. There will be injectivity issues. Timing also has implications on the resultant economics. So I think I gave an example last lecture when it was like when the oil prices were very high, people were fracturing like crazy, wells here and there, and their goal wasn't really to maximize the total production from the well throughout its lifetime. It was to maximize the total production right now, or the initial one. Because if you maximize the initial one, you are going to attract a buyer for your company that will pay you for your assets, basically. So it was a little bit of a conflicting objectives, which of course is to make money, but it's not in the same fashion. Let's put it this way.
I have a question, Professor.
Yes, sir.
So let's say if we have a reservoir that produce oil for 10 years, for example, how is the production will affect the temperature, the reservoir temperature? Like, are there a rate for the temperature?
Well, that reservoir, was it water flooded?
For example, the Balkan formation, like
yeah, Bakken is a little bit different because Bakken is shale, so you really don't inject much into shale. If you want to change, there is not much you can do to change the temperature other than when you inject some fluid to fracture, maybe the fluid you inject is cold, but it's not going to change the temperature for the long term. It's going to be for very little.
So basically, it's all about the pressure from the pressure temperature
not
envelope.
much you can do for the thermal unless you are using a thermal EOR method. Maybe you are doing electromagnetic heating. Maybe you are doing steam injection, stuff like that. But those really happen in the heavy oil reservoirs. That being said, it's a good point that you are making, because there is this old saying, heat can go where fluids cannot go. So if you find out that your reservoir will benefit by increasing its temperature, there are some things you can do. And I will suggest that you read the stuff that go on in Canada. So basically, when you have a heavy oil and you want to make it move, it's not easy to move. So you heat it up to make it move, right?
Reduce the viscosity.
Yeah, exactly.
And increase the viscosity. Yeah.
Decrease, lower the viscosity. Vaseline, for instance, which is a petroleum fluid, has 64,000 centipoise viscosity. And then water has 1. We used to do hydraulic fracturing experiments in the lab using, we wanted a very, very viscous fluid for scaling purposes. And we chose Vaseline, but we couldn't put Vaseline in our tubulars to inject. We had to warm it up. And when you warm it up, it starts moving, but as soon as you stop heating it up, it slows down. And then it's very hard to clean your palm and everything with it. Similar to, now what you are mentioning though, is how you can manipulate the temperature of the reservoir in terms of as a reservoir as a whole. That's why I asked if you are doing water flooding, because if you increase the pressure, you will affect temperature as well to some extent. Not by much, of course, but you have some control on the temperature. But mostly, you can assume that it's isothermal, like McCain did. I mean, and then worry just about the pressure most of the time.
Thank you, Professor.
Yeah. Data acquisition and quality control. Now, as I'm in the process of producing my well, I'm collecting data all the time and I do quality control to make sure that everything is going okay. Observations and measurements carried on the surface help practitioners understand well performance. This includes qualitative, visual, and auditory observations, along with quantitative, mechanical, and fluid-related readings. These are going to become clearer later on. Knowing the wellbore fluid position depth is required for evaluating the performance of an artificial lift system in context of IPR and VLP for a given well reservoir combo. So remember, well deliverability is a dynamic analysis between reservoir and well. What can the reservoir provide? What can the well facilitate? What flow can the well facilitate? So when there is not enough energy to bring fluids to the surface, you need to assist. And you are going to use what we call artificial lift. And in order to figure out what system to use for artificial lift, are you going to use a pump jack? Are you going to use an ESP, an electric submersible pump? Are you going to use a PCP, a progressive cavity pump? And so on and so forth. You need to know the wellbore fluid position depth. Like if the well is idle, not moving, where is the fluid level? Where does the liquid begin? And you are going to use sonic for that. You are going to shoot sound signals downhole and see how fast they come back. And then divide the time by 2, divide by the speed of sound under those conditions, and you get the fluid level. If you remember in drilling, we did something called static fluid level, which is basically how deep in the well my fluid can be so that it balances the reservoir formation point pressure. This one is a little bit different. I stop pumping, I stop flowing my well, and the fluid level stabilize inside the well, which suggests to me I do not have energy. The reservoir does not have energy to bring this to the surface. Okay, tell me how far it brought it up. Did it bring it by 10 feet? Then I need to use a small artificial lift system. Did it bring it by, is it like, I don't know, 3 miles? Then I need to use a more powerful artificial lift system. This is basically what I want to use. Also, what rates can we deliver? Because I don't want to put my well on ESP, electric submersible pump, which is something very important, very expensive, and very difficult to maintain and fix if it has problems. And then the well will be producing very small rates, and then I would be saying, oh, I wish I had put it on a pump jack. which is much more common and cheap and easy to fix, especially onshore. Tools developed and refined over time, like acoustic fluid level instrument or dynamometer for rock pumps. We're going to talk about those in the next module. But these equipment are used to diagnose what goes on in your well in terms of some items. And yeah, I mean, these are these tools are being improved and developed as we speak. So the instruments that our grandparents were using, or our grandparents' generation was using, is outdated today. We use better ones, and our kids and their kids are gonna use better ones, and so on and so forth. So, summary, what did we learn in module 4? We talk about formation damage in terms of fluid transport alteration, which is a more generic term. We talk about contributors of formation damage. We talk about how to mitigate formation damage. We talk about how do we quantify well performance or well deliverability. We talk about two-phase liquid and gas fluid flow patterns in vertical and horizontal conduits. Reservoir fluid classifications and phase behavior. And that was module 4. Homework is due on tomorrow midnight. Is there any question on the homework? If not, I'm available by phone, by email. Tomorrow I will start the office hours at 12:30 because I have a meeting at 11 until 12:15 or something. So I will send an announcement. The grades are online. Last time in the class, I wasn't certain they were online, but they were already online. I made a mistake. I posted them. I pressed the button that posts all of them early on. So, but I guess nothing bad happened. But yeah, the grades are online. Homeworks are due tomorrow. If you have any questions, reach out to me. And office hours tomorrow are gonna start a little bit later than usual, and I should be giving you this information soon. So thank you very much. Have a nice rest of your day. And I will see you all on Thursday when we are gonna start module 5, our last module.
Thank you, Professor. Have a good day.
Yeah, you too. See you, Shaber.